Hello everyone. Today we will talk about how we load balance our work. So not a load balancer for network traffic, more a load balancer for actual work that needs to be done. In our case, the enemy AI, for example, or in our case, our flowers currently. I have deployed everything to Minikube. There are some new scripts available in the root folder of the project which can deploy sort of the whole thing to Minikube. And the great thing about Minikube is that Minikube I can configure how strong the CPU and everything is, and it's actually weaker than my current PC. And what we do is we have the game configured to spawn 10,000 flowers, which is way too much for Minikube to handle currently. It won't be able to handle that great, but with load balancing, at least the game stays playable, and let's look into that. So last video we talked about the load balancer with primary secondary model. And now our primary is the enemy load balancer here, who runs and gives the load to the worker nodes. How this is done, we will later look in the video at the source code. But currently, it's waiting for workers, even though one worker is available. The reason for that is that this worker has too much work to do. And each update cycle takes this worker around 10 or 20 seconds, which is too much. Because after each update cycle, it will write its timeout value or its responsiveness back to Redis. And since it takes too long because the timeout is at 2 seconds or 10 seconds or something, it's too big and it is not a valid worker, and it gets all its jobs removed again. And this happens all the time. It gets the jobs, it removes them because it takes the worker too long to respond. What we can do now is, and that's the whole thing about why we developed it that way, we can scale up the workers. So now instead of one worker, we will have 10. And it takes some time, but we can look into what the load balancer is doing. When I can find it, here it is. Let's check the logs. And then we can see it moves the jobs around. What it does, new workers will register itself to the load balancer, and then those workers get control over certain enemies, which in this case is called jobs because it's usable for more than just enemies. And the thing is, some of them will take too much at the beginning, and then we have some rebalancing logic which will move the jobs around and certainly comes to a state which at least is playable. It isn't great, and it won't be great because this is way too much work for my small virtual machine to have 10,000 AIs running. But still, I want to show you that with this load balancer thing, the game kinda stays playable, and without it, you wouldn't even have a chance at all. So let me log into the game. So now I'm logged in, and let's go to the bottom, and we see all the flowers that have spawned. And it may take some time, but I can actually kill flowers, which you don't see the animation and everything. That's because network is starving for sending us the packages. But still, like I said, it's far from great, but those things still respond, which for 100% CPU usage, you might hear my notebook in the background and everything. This is awesome in my opinion. So let's go back and turn this down to a reasonable number, let's say 1000. I will pause the video, I will redeploy everything. But I think I will pause the video because this might take a minute or two. The document just got built and we got a new deployment and everything is deployed again. We have the load balancer again for the town, and it's waiting for workers. Let's check what the worker is doing. The worker is handling 1000 jobs and it looks like it takes too long. It takes about a second for this worker to handle the 1000 flowers. That should be playable. 1 second is far from great though. So when I go down, I get a lot of stuff which the backend had problems. You don't see the health bar because there are too many on top of each other, but sometimes you see them go down a little bit. But this is fully playable, but still one second response time is not great. So while everything is running, it takes even 3 seconds sometimes. Let's scale it again and make more workers available. Since I don't have limitations configured, that means the resource limitation is not configured, so the worker nodes aren't limited in how much they can go overboard when using CPU memory and everything. This test is not super great because if we limit the CPU per service, it would be even better. But still, we would have multiple connections to the Redis with more services, and we gain performance through that. So now some of them have more jobs and some of them have less jobs, but still most of them respond in a reasonable amount of time. Sometimes they need a second or something. Like I said, I didn't resource limit them, so they are fighting each other for CPU time. Still, this will most of the time increase the performance here, because we can now have bad luck and good luck. But if we resource limit each of them, and if we have a machine that is able to handle the work, then we will be able to distribute the work really good across multiple machines or one machine with enough CPU. But still, how did we develop it? I mean, this is an artificial test because everything is running on one machine without limitations. So since this is written multi-threading, it doesn't gain too much. Like I said, it gains a little bit on the Redis connection. And that's the performance we see here. And we see it get balanced really, really good. We see this service is responding in 50-100 milliseconds time, and we have the other ones also responding great. So this is balancing itself. The load balancer isn't configured really good because I played around with that a lot to test things to the limit. But what it does, it moves jobs around to as many workers as there are, and these workers could be different machines, and this is where we would gain great benefit from this. We need to check two services. One is the load balancer and one is the worker. Let's start with the worker because I think that's way easier. The worker itself just takes jobs that the load balancer is giving him, and we have a class load balancer worker which does all the magic. And the load balancer worker is just used, so you inherit from it. You give it a job type, which basically holds the metadata, like the spawn config in our case, and the name. And what your service will get, it will get those jobs as work. And then we have two things. We have two functions which can get called prepare update, which in our case will run before each job in the update cycle, and then you get a call for each job into handle jobs, handle load. This is how the worker works. It gets an update ping, and after the update ping, it gets for each job a request. At the start, it writes a heartbeat to the Redis, and the heartbeat in our case is just the current daytime UTC. So other one can check this daytime UTC and know when the last time this worker has responded. So after it wrote the heartbeat to the Redis, it prepares the update, which is basically our function that is called before the update cycle starts. And then for each and every job, we call our handle load function. And we do that in a multi-threading way. So we create a thread for each job, and at the end we wait for all threads to finish. Then we write the performance, the update duration to the Redis, and we write out how long the update took. Since I was a little bit lazy, this is updated after the update has run through. This means that this is always an update cycle late. That's why we saw sometimes 0 jobs, but still an update duration, which was quite long because the update duration is one cycle late. We could fix that, but for the diagnostic reasons, it doesn't make a difference. It's just for our output. We try to get our jobs, and the update cycle starts again. When the worker is new, or when the load balancer thinks the worker is not responding, then in both cases the job count will be 0. And if the job count is 0, we add ourselves to available worker for this load. So there is a list in Redis which worker is available and is able to get load. This is everything the worker does. It gets the jobs. If the job is 0, then it adds itself to available worker. It adds itself as a unique value. So if it's already in there, nothing will happen. So the load balancer on the other side will be the different side. It will work with the list. First of all, at the top, it's configured to have a rebalance cost of 50 milliseconds. And the max rebalance per update of 1000, which is ridiculous, of 10,000, which is way too high. We talk about those values shortly. So when I become the primary, or when I'm the primary and an update cycle of the primary is happening, then we do balance load. And the first thing we do is we update our workers. And what it does, it gets all workers from this worker list where the workers add themselves unique, and it checks the performance of those workers, and it also checks the heartbeat. And if the heartbeat of those workers is not fine, the load balancer will remove this worker from the list. So workers itself add themselves to the list, and if the load balancer says this is not okay, this worker is not responding anymore, then it will remove the worker from the list. So when the worker recovers and responds again, it has 0 jobs, and it will add itself, and the system will then start working again all over. And this is all what this update worker does. It reads the performance of every worker. We need that later. And it will keep that in a list as caching mechanism for us to work later with that. And it will remove every worker that is not trustable because of their heartbeat. So after that, we have a valid list of workers which are good for getting jobs. And first of all, we free every job that a worker that was responsive and is not responsive anymore. Let's say we have a worker, let's start, say, the beginning of our test, we would have 10,000 flowers, and this one worker took way too much time to be able to handle that, and he got removed from the load balancer, from the worker list. Then of course all of those jobs that this worker was handling are now not handled anymore and will get removed from this worker. This is what this does. It unassigns the untrusted worker. So for every untrusted worker, we unassign all jobs from this worker, which basically is clearing the list of the job list of that worker. And then we remove this worker from our caches and everything, and also remove this worker from the worker list, which we are going through now. So when we have no trustful worker, then we message out waiting for workers, and we return, because we can't do anything without any worker. So when workers come up, then we do our first load distribution. Load distribution works like that. We go through every worker, and we get a list of assigned jobs to those workers. The reason why we do that, and we don't have caching and everything in place for that, we always read in every update cycle from the Redis, is because our primary load balancer server could crash and the secondary could take over, and we don't want the secondary that becomes the new primary not to go through the load and assign all jobs all over the place. We want him to start working with the job the old primary did, and not. So let's say we have two workers, and the load balancer assigned 50% left and 50% right to those two workers, and the primary dies and the secondary takes over. He will do basically nothing, because he will see that all jobs are assigned and the workers are happy and everything. So this is why this whole load balancer code here is running through stateless. So each update cycle, it reads everything back from Redis and works with that. This is not performance-wise a good idea, but for our case, its reliability is more important than performance, because let's say performance is not great on load balancing side. It doesn't matter if it takes a second or two longer to move the jobs around. The important work is done by the worker itself and not by the load balancer. The load balancer is just distributing the stuff. And if that takes a second or two longer, it's not a big deal. It's more important than that this is reliable, and we don't move jobs around where it's not needed. We only want to do that if it's needed. So even on a primary to secondary switch or load balancer side, the behavior is the same, which is more important than performance here. So we write that to our cache. This cache is just for one update cycle. It gets updated every time. And then we just update our cache with what the worker has for jobs. So it's one time worker to assign jobs, and it's a cache from each job to each worker. After we have gone through all workers, we check which jobs aren't assigned at all. So we go through all jobs and check if they have a worker assigned to them, and if that's not the case, we have unassigned jobs. So we have assigned worker jobs, which is worker to list of jobs. We have job to worker, which is which worker is assigned to each job. And then we check for each job that we are currently tracking if if he has a worker. If not, then he is in unassigned jobs. So with that, we have our whole configuration. And then we calculate some matrices, which is basically we calculate the average job duration, the worker count, and the average worker duration. So we go through every worker and check how much worker works, how much jobs this worker has, and how this worker is performing, and then we have a worker performance divided by jobs. That's the average job duration, and we add these values together for every worker, and then we have an executing worker count, which is the worker count of the workers that really are executing job and no idle workers. And then we have the average worker duration, which is just the update cycle performance they wrote to Redis. With that, we basically have a zero division check here, because when execution worker count is 0 and we want to have the average of that, it's a division by 0, and then we just return those values as 1, which is a lazy trick to not have a 0 division. And since we added the average worker duration here for each worker, the next thing we need to do is divide that by the count to have a really average for one worker and not for the whole worker list. And the same goes for the worker duration. This is a simple mathematics here. And then we have those average values, which we need for rebalancing. So when the metrics are calculated, the first thing we do is we assign unassigned jobs. That's the easiest thing to do. We have created this list with unassigned jobs, and we go through the unassigned job list, and we search for the fastest worker. And the fastest worker is, if we have just one worker, it's this one worker, and else we get the performance values, min value, and get the worker by performance. This also means that most likely when we assign those jobs all get assigned to one worker, because one worker is the fastest. We could limit how much this worker will get from the start, but usually when the system starts, we have 1 or 2 workers and it assigns everything to the first worker, let's say, then the rebalancing will in the next update cycle kick in and rebalance it. So kind of lazy here. We should normally not assign them to just one worker, more maybe round robin or something. We could implement that, but still it works good enough. And we assign everything to that worker. We get the fastest worker every time, which is stupid, because nothing will happen in this update cycle. But this is for round robin, so we could again get the next fastest worker but exclude this worker or have an index or something. But we will do that. That's why we do it. Get it every time. Currently, we could do it outside, because while this loop is running, the performances don't update. But still, we assign the unassigned jobs. That's the more important part. And then the rebalancing. This is where the complicated things come. First of all, if we don't have any worker, then rebalancing will not do anything, which shouldn't be the case, because this check is before here already. But I like sometimes to have my functions, or when I have tests and everything, calling the functions. Sometimes I have such double checks. I think Performance-wise, this is neglectable, and on the other side, it makes the code more robust. You shouldn't do that too much, but I think this is fine here. So first of all, rebalancing each update cycle, our load balancer picks the slowest worker and picks the fastest worker, and it tries to rebalance between those. So we don't do a full rebalance, so each update cycle jobs can move around from the slowest to the fastest worker. And this is everything we do each update cycle, and let's say we have 4 workers, 1 to 4, and 1 is the slowest and 4 is the fastest. Then it will take half of the jobs of the slowest, limited, clamped to max value, which we will talk about later, and will move those jobs to the fastest worker. So let's say those two are now balanced fine. Next update cycle, worker 2 is the slowest and worker 3 is the fastest. It will balance between those, and as you can see, it will balance around, and with more update cycles everything will be fine. So the balancing is really cost intensive. What that means is it moves the job from one worker to another, and jobs also register for events for those certain enemies in our case. So let's say when I attack a flower and if the flower gets damaged, then this damage is applied by the worker. And the problem with that is that there can be hiccups up while we do rebalancing. So we don't want to rebalance all the time. That's why we have a rebalancing cost. So let's say, let me write an example really fast. Let's say we have worker 1 with 20 jobs and takes 10 milliseconds for him to do his job, and we have worker 2 with 40 jobs and he takes 20 milliseconds. There is actually no need to rebalance that because this is totally fine. What we have is a rebalancing cost which we can configure, which is currently 50 milliseconds. So what we will check if the average duration plus rebalancing cost is bigger than the slowest performance. So in our case, average worker duration will be 30 because it is 15 because it is 10 milliseconds plus 20 milliseconds divided by 2 with the right parentheses. So we have a 15 millisecond duration, and 15 milliseconds plus 50 milliseconds rebalancing cost means we have 65 milliseconds rebalancing cost, and this is bigger than our slowest because the slowest takes 20 milliseconds. So 65 milliseconds is bigger than 20 milliseconds. We don't need to rebalance. That's how math behind that works. So let's assume this worker has 100 milliseconds. Then average worker duration will be 55, and 55 plus 50 is 105, and 105 milliseconds is still greater than 100 milliseconds. So let's go through that again because I messed up. So 210 is 105, 105 plus 55 is 155, and 155 finally is not bigger than 200 milliseconds, and then we will rebalance. This is just some mathematic behavior to not rebalance all the time, to have some kind of configurable value when a rebalancing will happen. Another check which we do, if the fastest worker plus rebalances cost is slower than the slowest worker, we also don't rebalance. So if that difference is is not big enough, for let's say again our 10-20 milliseconds thing, so fastest workers 10 milliseconds plus rebalancing cost is bigger than 20 milliseconds, we don't do anything. So if this again is here, let's say 100, then this check would be false, and we will start doing rebalancing with this check, but this check also fails. So those two checks make sure that we only rebalance if the fastest and the slowest worker really have a great distance. But so the right check makes sure that fastest and slowest worker have a significant performance difference. And this check makes sure that we only rebalance if the average worker and the slowest worker has a significant performance difference. That's the whole logic behind that. But if that is the case, then we will check how much jobs do we move. And what we do get, we get the assigned worker jobs from the slowest worker, half it, so half of the jobs we want to move, but still we clamp the value to a maximum value of, which was 10,000, which basically moves everything all the time, but this time it's 1,000. So it takes whatever is slower. If whatever is smaller, the half of the jobs or our max value, whatever is smaller, get moved. If we have nothing to move, which can happen, then we don't do anything. Which can happen when the slowest worker at the beginning has no jobs and is for some other reason slow, which I can't make my mind up why that should be the case. But still, for example, when the system boots up and everything, this will happen. So, and then we write out that we will rebalance stuff from source to target with a amount of jobs that we want to rebalance. Then we go through that jobs, we remove them from the slowest one. We remove them at the last index. The reason for that is we have a stable value, a stable part of jobs that don't get moved around too much. And that's why we remove from the right side. Let's check how a list functions. Let's say worker 1 has job 1, 2, 3, and 4. And worker 2 has job 5 and 6. So let's say we rebalance 2 jobs from worker 1 to worker 2. Then job 3 and 4 are moved. Let's say again we have a very bad state and worker 2 now wants to move jobs to worker 1, then again job 3 and 4 get moved. This will make sure that we don't shuffle around everything all the time. So if you think about it, if we shuffle around the first jobs, let's say 1 or 2, and then we shuffle around 5 and 6, and we add them at the bottom obviously, and we shuffle around 3 and 4, you see every job shuffles around, so it's more convenient to shuffle from the end of the list instead of from the top. So what we get the first job that we want to move, and we unassign it from the one worker source and we assign it to the other worker, and we update also our cache. And since we know that how long an average job is, we also update our performance cache, which is which doesn't do anything because our thing ends here anyway. But this is how we balance currently the work, which works extremely good. So there, if we have a case where everything is handleable, it will scale pretty well across everything. And this is everything I have for this week. I really want to thank my patron Julian for supporting this project. I wish you all a great week. Bye.